So this is afternoon session and also extra session. So a very warm welcome to the extra session of our Big Data System course. Yes, actually we have not covered a few concepts. So in this extra class, we will try to cover the syllabus of 11th session and also 12th session. Okay, welcome back everyone, guys. So we are officially in session 13 actually. So tomorrow I'm going to conduct session 13. But yeah, we are looking at 11, session 11 and also session 12 concept. Let me share my screen. Yeah, this is what I was talking about. And which is all about storage on cloud and cloud computing, so on and so forth. Okay. And in storage on cloud, we are using AWS examples. Yes, my dear friends, if you want to build a big data system today, so whether it is for a startup or a large enterprise or a research project, the very first question you ask is no longer, so which server should I buy? But rather, which cloud provider should I use? Correct? No. So cloud computing is the fundamental infrastructure layer that enables the scale, elasticity and cost effective required to handle big data, volume, velocity, and also variety. So over these two sessions, so we are shifting our focus from the theoretical concept of distributed system and on-premise big data framework like Hadoop to the modern cloud native way of architecting these systems. So get ready to learn how to design a big data systems on cloud. And I think you people have AWS access, right? So do you have AWS access? Yes, no one is responding. So do you have AWS Access? Yes, by using AWS Access also, you can install the instances, whatever you want, and then you can complete your assignment work. But better you people use remote tools, okay, whatever we are providing, virtual tools. And yes, guys, so what I would like to say now is, so this is a very important point, guys. So everything we discussed about Hadoop, NoSQL, and distributed algorithms is now being applied on top of cloud platform. Okay, the cloud is the foundation. So in what today's session. Okay, so let me start here. See, this is the second slide. 1 second, guys. So where are we in the course? Guys, so let's quickly anchor ourselves in the course material. So we have covered a lot and it is all building up to this moment. So first we started with the basic concept. So you just remember, guys. So we have discussed about LOR, right? That is the locality of reference. Okay, and the different caching strategies, understanding parallel and distributed systems, and grasping metrics like performance and availability. So that was the what theoretical foundation we have learned in the previous sessions. And then we move to advanced concept. Okay, so advanced concept like distributed programming design. So this is where we got into the complex world of distributed programming design and looked at different consistency models like eventual consistency, and of course spent quality time debating the famous CAP theorem. So we have discussed about CAP theorem also. There we have discussed about consistency, availability, and partition tolerance. And you just make a note of this, guys. The CAP theorem will resurface in our discussion of cloud storage later. So this is again important in cloud computing also. And next, yes, we delved into the Hadoop ecosystem and we understood file-based batch processing system. So that is by using MapReduce. And also we have learned HDFS concept. It is nothing but a file storage system. And we have learned about HBase. It is nothing but database. Workflow we have learned. Coordination system like Zookeeper we have learned. Okay, so we then explored NoSQL databases. So recognizing their key value, document, graph structure as ideal for handling big data variety. So now, guys, So we are here. So we are talking about cloud compute and storage options. Okay. So our goal is to use everything we have learned to design a robust, scalable big data system on the cloud. And finally, so we will conclude with in-memory streaming system, that is Spark, in the session following. And you see, guys, the learning path is logical from theory to on-prem distributed systems and now to cloud native big data architecture. Okay, so now that we know where we stand, so let's focus on the agenda for today's session. So this is the 3 points I mentioned here, guys. Yeah, first we are starting with cloud concept. So maybe you are all aware of this. So here we are starting with the fundamentals. We are learning what is the cloud and what are its models and characteristics. And we need a standardized definition. So we are all speaking the same language. And next we are talking about compute and network. So this is the core engine of any cloud platform. So how do we launch virtual machines or containers? And how do we connect them securely and efficiently? And we will cover this today, guys. So while storage will be the focus of the next session. And last one, we have a best practices. So theory is one thing, but applying it successfully is another. So we will be looking at the architectural best practices for building scalable, resilient, and secure applications on the cloud, especially big data applications. So this is where you learn how to design for failure and achieve true elasticity. So guys, so let's start with the most basic yet most important part of our discussion, that is the formal definition of cloud computing. So let me see your chat box, guys. So what exactly mean by cloud computing? So I think already you have learned this definition, right? So what do you mean by cloud computing, guys? Any standard definition you know means please type on chat box. See, we all know, right? When we talk about cloud computing, we are not just talking about someone else's computer. So we need a precise definition. Is it the industry standard, the most widely accepted one? So from where we are going to take the cloud computing definition, guys? So anyone? So mainly it is comes from the US National Institute of Standard. Correct? No? Yes or no? NIST. So we are going to call it as NIST. So NIST defines cloud computing as, so this is the complete definition, guys. A model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interactions. Guys, now see, you just look at the colors. So I'm going to break this complete definition into few important points. So the very first point I'm taking here is, so ubiquitous, convenient, and demand network access. Guys, what is the meaning of this? Can anyone tell me? I'm not getting any responses from the students end. Yeah, I got a definition now. So what is the definition? What is the meaning of ubiquitous, convenient, and demand network access? Hmm? So the meaning of this is you can access the resources anytime, anywhere, and with just an internet connection. Correct? No? So think of it like accessing your emails. So it's always there, right? So that is called as ubiquitous, convenient, and demand network access. And what about the second one? So second, I'm breaking this into one more point here. That is shared pool of configurable computing resources. Guys, actually the provider. So who is the provider? See, AWS is the provider, is it? Azure is the provider. And you can say GCP also. Guys, the provider has a massive pool of physical hardwares. So we can get servers, networks, storage, applications, services. So this pool is shared among many customers and the resources are abstracted and configurable. So you can select your CPU, RAM, data size, disk size, whatever you want. Correct, no? And one more point I've taken here is, so rapidly provisioned and released. Guys, this is the magic. So you can launch 100 servers in a minute and shut them down just as fast. Okay, the speed of scale is key to big data's velocity challenge. And finally, I have taken one more color here. So that is in blue. One more sentence in blue color. So minimal management effort or services provider interactions. Guys, you don't call someone to install RAM or you don't call someone to install operating system. You click a button and run a script. The cloud provider handles the entire process automatically. So this automation is critical. Okay, guys, what I would like to say here is, see, this complete definition is giving you what? All the meaning of cloud computing. Okay, so this NIST definition leads us straight to what is known as NIST 3, 4, and 5 rule of computing, cloud computing. So make a note of this framework, guys. So it is essential for any cloud interview. Correct, no? So it stands for what, guys? See, here we have mentioned 3 cloud service models, 4 deployment models, and 5 essential characteristics. Correct, no? So now what we are going to do, guys? So we are going to start detailing the 5 now. So the essential characteristics. See, next slide, I'm showing you the same thing. My dear friends, so these 5 characteristics are what truly differentiate the cloud from traditional hosting. What is the first one here mentioned? On-demand self-service. Guys, this is the key, right? The user can provision computing capabilities like server time or network storage automatically without requiring human interactions with the service provider. So that is called as on-demand servicing. And what about broad network access? The second one is ubiquitous network access, right? The capabilities are available over the network and access through the standard mechanism. So typically we are going to use internet here. Okay, so this internet promote use by heterogeneous client platforms. So you can use mobile phones, laptops, desktops, or PCs to what access all these networks actually. And what is the next one? Next one is resource pooling. Okay, location transparent resource pooling. Guys, the providers computing resources are pooled to serve multiple consumers using multi-tenant model. Guys, you just imagine the resources like storage, processing, memory, and network bandwidth. So these are all dynamically assigned and reassigned according to consumer demand. Correct, no? So I can take one analogy, guys. Imagine a public library. Guys, in public library, the books are shared among all the members from a common and large collection. So that is called as resource pooling. Okay. And what is the next one? Next one is rapid elasticity. So this is the big data enabler. So capabilities can be rapidly and elastically provisioned to quickly scale out and rapidly release to quickly scale in. Okay. So scale out means you are going to add more resources. So scale in means you are going to remove resources. Okay. The resources appear to be unlimited to the user. So let me take one example to explain this, guys. So during the IPL final, a streaming service needs 1,000 servers. Would you agree with this point? Correct? No, it scales out. So after the match, it scales back down to 50. So this is rapid elasticity, guys. And the last one is measured service with pay-per use, or we can call it as measured service simply. Guys, cloud system automatically control and optimize resource use by leveraging a metering capability. So you only pay for what you use. and means the resource usage can be monitored and reported transparently. So this is pay as you go model. Guys, understanding these 5 points is crucial. So next we move from characteristics to the different ways the cloud can be deployed. So I think this is crystal clear to everyone, right? All these points are crystal clear. Shall I get quick responses on chat box? Yes. Okay. Thank you. Okay, guys. Now I'm moving into next slide. See, 4 deployment models. My dear friends, so 4 in the 3 to 4 rule refers to the different ways cloud infrastructure can be deployed. Okay, what are those, guys? The very first one is public cloud. Maybe you are all aware of this public cloud. This is the most common model, right? So the infrastructure is made available to the general public or a large industry group. And also it is owned by an organization selling cloud services. So I can take the example as AWS, Azure, so GCP. Okay, so think of it as a what massive shared apartment complex run by third party. So where anyone can rent an apartment. See, apartment. See, usually I will take this example, guys. That apartments are nothing but VMwares. Okay, VM services. So it offers the lowest cost and the greatest scale. And what is the second one? The second one is, this is the first one, public. The second one is private cloud. Guys, in private cloud, the infrastructure is operated solely for an organization. So it can be managed by the organization's own IT staff or a third party. And it can exist on premise or off premise. So I don't want you people to explain this with an example, right? The best example for this is a major banks, government agencies. So runs cloud environment just for its employees to ensure maximum security and also control. They use cloud technologies like OpenStack and VMware internally, guys. And what is the third one? The third one is hybrid cloud. So hybrid means, you know, right? So this is a what composition of 2 or more distinct cloud. Either you can take private clouds or you can take public clouds. And these clouds remain unique utilities, but are bound together by standardized technology that enables data and applications portability. So example for this is a company runs its sensitive customer data processing on a private cloud, but uses public cloud to host its burstable high traffic website during what sales seasons. So they connect what two securely. That is called as hybrid actually. And what is the last one? The last one is community cloud. Guys, this is an infrastructure shared by several organizations and support a specific community that has shared concerns. The shared concerns could be a common mission. Similarly, security requirements or compliance considerations. So let me take one example to explain on this, guys. So let me take one healthcare. So guys, you all know, right? Healthcare providers are research universities sharing a cloud platform for collaborative research projects. So where data governance and regularity compliances are critical and shared requirements. Guys, these models allow organizations to pick the balance of control, the balance of cost, security, and that works best for their big data system. So now let us look at the service model. So can you guess what are those 3 service models? Yes, let me see. Anybody is going to respond on this. So what are the 3 service models we are going to use, guys, in cloud computing? Yes, it is perfectly correct. So my dear friends, the 3 in our 3-4-5 rule represent the 3 main ways cloud providers offer their services. So often visualized as what, guys? Stack. So these are known as the 3 layers of the cloud. We can call it as a what? 3 layers of the cloud. So what are those, guys? The very first one is, as you told, it is IaaS, and second one is PaaS, and third one is SaaS. So these are the three layers. So think of it like what getting a pizza, guys. Okay, I will always take this example to explain in my physical class. So let me take the very first one. So what is that first one? SaaS, software as a service. Guys, you buy a complete pre-made pizza. The meaning of this is you are going to purchase the entire application. Okay, and you just eat it. That is called as SaaS. And what about PaaS? Platform as a service. Guys, you buy a pizza base, sauce, and pre-cut toppings. You need to cook it yourself, but you don't worry about the duff. So here, cook it yourself means what, guys? Run your code. So you're not worrying about duff means it is nothing but operating system and network that is left to the cloud providers. And what is the last one? The last one is IaaS, infrastructure as a service. Guys, to buy the raw ingredients, see, you have to buy flour, yeast, tomatoes. Correct? Now, these are all ingredients, right? You manage everything from building the oven. So oven is nothing but operating system and virtualizations to cooking the pizza. So this is the best example I can give to explain always for this cloud services model. And we are going to see how these service models are absolutely vital for big data application in the next coming slide. I hope this definition is clear. I'm not going to explain more on this, guys, because already you all know about this. So now look at here, guys. So next slide, I'm explaining you on. So cloud services for big data. My dear friends, so why is the cloud an ideal platform for big data? Correct? No, guys, it is simple. Cloud computing follows the same distributed cluster models as big data. Okay, that is the very first point I have mentioned here. Look at here. Okay, so both rely on what, guys? So both rely on a huge number of interconnected computing devices. So let's see, guys, how our three services models fit into the big data context. So the very first one I'm taking here is infrastructure as a service. Guys, this provides the fundamental building blocks. What it is providing? It is providing huge storage and computational powers. You get access to virtual servers and raw storage. Okay, so what is the big data benefits then? Guys, you have to answer for this, right? Guys, you get the limitless storage and computing ability for your big data. You can provision thousands of virtual machines. Okay, so virtual machines like what? EC2 instances in AWS. And petabytes of object storage. It is nothing but AWS S3 to meet your needs. You install Hadoop or Spark yourself, but you get the elastic infrastructure underneath. Okay, so let me look at what's the second one, that is platform as a service. Guys, the vendor provides a ready to use platform environment. Okay, then what is the big data benefit? What is with respect to big data? Guys, this is the lifesaver. So vendors offer platform that come ready with Hadoop and also MapReduce. So think of AWS Elastic MapReduce, guys. So we are going to call it as EMR. You simply say, I need a 20 node Hadoop cluster. That's it. The cloud builds it, installs all the software and manage the operating system. So it saves the hassles of installations and also management of these complex environment. That is comes under platform as a service. And what is the last one? Software as a service, right? So this is the end user application layer. The vendor provides an out of the box solutions here. So with respect to big data, what is the benefit? Guys, this is the great for organizations that need specialized common software for big data without building it from scratch. Okay, let me take one example to explain on this, guys. You just imagine, so we have XYZ company. So this XYZ company needs to monitor customer feedback and analyze sentiment from social media posts. So this is the problem statement. Guys, instead of building a whole analytics pipeline, they can subscribe a social media analytics SaaS solution. Correct, no? So is this not interesting, guys? So this is the cloud services for big data. So I hope everyone understood all these 3 points clearly. Is this clear? Is this clear? Yes. So now that we know the what models, now let us look at the what key players in the big data cloud space. So what are the key players, guys? Look at here. I have mentioned here. Cloud providers in big data market. Guys, look at here. So big data cloud market is primarily dominated by 3 major players. But there are many smaller ones as well, guys. But I'm taking the what major 3, that's it. Okay, let's look at the key big data services they offer. The very first one is Amazon. Amazon Web Service, AWS. Okay, guys, AWS is the market leader. So their big data portfolio is immense, guys. So under that, the very first one we have EC2. It is nothing but Elastic Cloud Compute, Compute Cloud. Okay, this is a what? Which layer it is, guys? So this is IaaS what layer? Correct? No, the virtual machines. And what is the second one? The second one is EMR, Elastic MapReduce. So their flagship. So this is comes under PaaS. So the flagship platform as a service for running managed Hadoop and also Spark clusters. And we have Kinesis also. So Kinesis is a what real-time data streaming and processing service. And we have DynamoDB. So this is also providing by AWS. Okay. So this is a fully managed high performance NoSQL key value database. And we have Amazon S3 simple storage service. So this is highly scalable object storage service, guys. And last one, we have Redshift, a fully managed petabyte scale data warehouse. So all these are provided by this Amazon. And next, what is the next one, guys? Next one, GCP. So Google Cloud Platform. See, Google leverages its internal technologies, guys. So the very first one is Google Compute Engine, Google BigQuery, and third one is Google Prediction API. What is Google Compute Engine, guys? So this is IaaS, right? So their IaaS offering for what? Virtual machines. And Google Big Data Query, BigQuery. So this is highly scalable serverless enterprise data warehouse. So see, it is very much similar to this Redshift, but with different architecture. Architecture is different. And the last one is what, guys? Google Prediction API. So this is mainly useful for machine learning and predictive modeling. So useful for predictive modeling actually. And what is the last one here? The last one is Windows Azure, or we can call it as Microsoft Azure. Guys, Microsoft offers a strong suite, especially for enterprises. So the very first one is Azure PaaS Cloud. So this is built around Windows and SQL technologies. And the second one is Windows Azure HD Insight. So they're fully managed Hadoop distributed system. So this is Hadoop distributed system. Guys, all these 3 offers a comprehensive set of services covering all your big data needs. To make this tangible, so let's look at what real world examples from the financial world. So shall we take one real-time example, guys, to explain on this? So if you are saying yes, then I will take the example, guys. So yes, I think I have 2 examples. So I'm not going to explain you 2 examples. Instead of that, I will take one example. So which one you want, guys? You look at here. So both of them, all of you look at here, guys. So one case study I have on NASDAQ. Another one is on social media analytics. So which one you want? Which one I want to take up now? I will go with majority. Social media. Okay, then NASDAQ people will check it later, right? Okay, I will go with social media analytics, guys. Okay, this one I'm giving you as a homework. So after completion of this, you just go through this. Okay, let me take social media analytics. Guys, this is one of the another key big data challenge. Social media analytics. Guys, this is all about what, guys? This is all about velocity. Okay. So velocity means what? Ingesting. Let me write here. So ingesting, processing, and analyzing massive streams of data in a real time as they are generated. Okay, imagine you are running a major e-commerce company and you need to monitor Twitter, Facebook, and news sites for mentions of your product. Guys, you need to know now if there is a what crisis or viral trend. Correct? No? This list means this slide list 4 placeholders. So which represent these steps in a what typical real-time cloud architecture. What is the very first one? The very first one is data from a variety of sources. See, look at here, data from a variety of sources. Guys, this is the injection layer. Okay, pulling data from social media APIs, logs and click streams, etc. So this is Amazon Kinesis data streams. And next to that, so we have streaming injection service, streaming ingestion services. So this is typically a managed service like AWS Kinesis. Correct? No? So Kinesis is built to ingest and process massive continuous streams of data. Understanding my point? And what is the third one? The third one is real-time processing or real-time analysis. Guys, the data is processed on the fly. See, let me take the example of sentimental analysis, otherwise filtering. Understanding my point? So here, the data is processed on the fly using services like Kinesis Analytics, or you can use Spark Streaming running on EMR. Okay, and last one is what, guys? The last one is storage. The last one is storage, or we can call it as query. Storage or query. Guys, the processed data, see, already it is processed. So now it is stored in a fast NoSQL database. So let me take the example of DynamoDB. So we have stored everything on a DynamoDB, or we have stored everything on a Redshift. So Redshift is the best example for data warehouse, right? See, why we have stored all this data, processed data inside this databases? Because we have to perform some queries by business analyst. Otherwise, we are going to what perform some SQL or other queries. So that is happened by business analyst. So in that situation, we are going to use this. Guys, this architecture is entirely enabled by the cloud ability to provide scalable, managed streaming, compute, and storage services. And it is truly a cloud native big data solution, guys. I hope this example is crystal clear to everyone. So is this clear? This example is crystal clear. Guys, just now we have seen the power of the cloud. So now let us have a balanced discussions on the pros and cons of your cloud system. Okay. Yes. So next slide is discussing on pros and cons of cloud system. Guys, very first thing is I'm going to start with the advantages, pros. So pros of moving our big data system to the cloud. So the very first point, look at here, guys. The very first point is cost effective in specific cases. So this is a huge one, right? So it is especially cost effective for short term projects or experiments because you avoid the huge capital expenses of buying physical hardware here. And you convert what? you convert cap expenditure into operational expenses. I hope everyone will agree with my point. You must, however, be clear about your usage to keep cost in check. So let me take one small example to explain this, guys. Guys, you have a research team. That research team needs 50 high CPU machines for 2-week simulations. On the cloud, they pay for 2 weeks. On premise, so they have to buy what 50 machines that sit idle 95% of the time. I hope you are all understanding what is cost effective in specific cases. And the second advantage of using this is no in-house capability. So this point already I've explained you. The second point you have to observe here is no in-house capability. Guys, if your organization lacks the specialized manpower to build and manage a huge data center, the cloud solves this problem instantly. Okay, that is called as no in-house capability. And third advantage of using this is reliability. Okay, you shift the onus of uptime onto expert providers. Guys, AWS, Azure, GCP have thousands of engineers, thousands of tools, systems dedicated 24/7, ensuring high availability and also fault tolerance. So they manage the backup and the recovery for you people, guys. That is one advantage. And along with that, we have one more advantage. That advantage is called as scaling. Guys, this is the core benefit of big data, right? See, since the very first class, I'm telling you scaling. So you get about storage and compute scaling as required. Okay, you stop guessing capacity, guys. No more over provisioning or under provisioning. Understanding my point. And one more very, very important point, what you have to see here is, our advantage, what you are going to see here is global data centers. Okay, global data centers. We are going to call it as DCs. Guys, you can deploy your applications to global DCs that are accessible from anywhere without having to own a single one. So this is perfect for global applications. Okay, now let us see what are the challenges or cons of using this cloud computing. Okay, right hand side, we have mentioned cons here. So the very first cons, see now for the cons, the challenges and the risk of moving big data to the cloud. The very first challenge is security needs rethinking. Correct, no? Guys, the traditional enterprise security model based on a what? Perimeter and does not work on the cloud. You need to rethink security for data on your cloud. You need a shared responsibility model where the cloud provider secures the underlying infrastructure, but you are responsible for securing your data, securing your application, securing your configurations. So this is a very important point, right? This is one concept of using your cloud computing on big data. And the second one is need to depend on external providers. Of course, yes, right? You are now dependent on the what third party for your core infrastructure and also applications. So if they have an outage, you are impacted. That's all. And the third cons here is vendor lock-in. Yes, one of my friend was asking on this question. What do you mean by vendor lock-in? Guys, if you heavily rely on single providers, proprietary services. See, for example, you are depending on DynamoDB. You are depending on BigQueries. So that is called as proprietary services. Guys, this becomes very difficult and expensive move to the different cloud later. You are locked in. That's all. Okay. And the last point is not cost effective if not well planned and tracked for usage. Correct? No? While cost effective if used correctly. The cloud can become a massive money sink if not properly managed. You need to track usage and plan well to avoid the unexpected huge bills from idle resources or excessive traffic. Okay, so it is a trade-off, guys. So we need to be what? Strategic. So now let's revisit our session plan and dive into architectural details. I think till here everything is clear. So pros and cons is crystal clear to everyone. Am I right, guys? Is this clear? Okay, yes. Now look at here, guys. Next, I'm moving to the what next topic of today's session. So, guys, a quick what check on our map. So we have covered cloud concept, the 3-4-5 rule, big data fit, pros and cons. So now we are transitioning into the core discussions of compute and network. Okay, we are discussing on the second point, compute and network, and then we will cover best practices. Okay, guys, on the see here, you see a simple see. Let me show you the diagram. See, look at the diagram. So this is showing basic IaaS architecture. Okay, so this is a simple diagram, guys. Simple diagram showing basic infrastructure as a service architecture. You just remember, guys, infrastructure as a service is what? So this is the fundamental layer, right? So where you manage operating system, but the hardware is virtualized. Guys, in a simplest form, an infrastructure as a service cloud is a collection of servers, network switches, storage arrays managed by hypervisor. So usually, so for hypervisors, we are going to use KVM or we are going to use Zen systems. Okay, that enables the what provisioning of virtual machines on the demand. So this basic architecture, which is exemplified by open source platforms like OpenStack. Okay, so that is the foundation upon which all the complex big data services are built. So now look at the structure of a major cloud providers. So that is AWS structure. Okay, so my dear friends, let's use the what AWS architecture as a practical example to understand how a cloud provider organizes its resources for scale and reliability. Okay, so the very first point I'm explaining you here is region. I think you all know about region, right? Region is what? A region is a physical geographical locations in the world where the cloud providers has cluster data centers. So can you give an example on this, guys? Already you are all aware of this, right? So can you give an example for regions? Yes. What are the examples for region? US East. Correct? No? Yes, US East. And then Asia Pacific. Correct? No? These are all the best example. South Asia, Asia Pacific. So it is available in which place, guys? In India? Mumbai, right? So what about US East? US East. It is in Virginia, is it? Yeah, North Virginia. Exactly. Guys, regions are completely independent of each other for maximum failure isolation. Okay, so that is regions. I think you are all aware of this. And the next one is availability zone. The second one is availability zone. We can call it as AZ also. Guys, a region is split into multiple availability zones. Okay, so this AZ is one or more distinct data center. So they are designed to isolate failures. And AZs within a regions are connected by low latency, high redundancy network. So this is a very important point you have to remember, guys. If one AZ goes down, the other in the same regions remains unaffected. So your big data system should span multiple AZs for high availability. And the third one is compute instance. Sorry, guys. Guys, this is your actual computing unit. Okay, our actual computing machine, our VMware, our container, or even a function, FAAS. Usually we are going to call it as FAS. Okay, so these instances can be started from pre-configured images and can have elastic static IPs for consistent addressing. And next one is attached volume. Attached volume, maybe you are aware of this, right? So this is a block storage that can be what connected to the compute instance and serving as a local file system. So usually guys in college, so we are having a notice board, right? So this attached volume is like a notice board. Okay. And the best example for this is AWS EBS volume attached to the EC2 instances. And next one, we have external storage. Okay, this is the large remote raw data storage like S3. The best example for this is S3. So remember what? NASDAQ example. So there we are going to use what petabytes of data live and decoupled from the compute. Everything we are going to store inside the external storage. Okay. So now along with this, so we have security groups also. So these are the what instance level virtual firewalls. So there are rules created. See here, we are going to create some rules to control the network access to compute and also storage instances. You just make a note of this, guys. So security groups are stateful. Correct, no? Security groups are stateful. So network ACLs are stateless. That both of the concept we will discuss later, guys. So I will explain you later. So now we have one more point that is called as load balancing. Guys, a service used to distribute incoming application traffic across multiple compute instances, often deployed across different AZs for fault tolerance. And next one, we have elastic scaling. You know the meaning of elastic scaling, right? So this is a mechanism that automatically or manually creates or deletes the compute instances used on demand. So this fulfills the rapid elasticity characteristics. And finally, we have backup recovery. So you can take snapshots of your volumes to preserve the state. So which is very much crucial for data recovery, guys. Guys, and one more thing I have not taken here, that is nothing but DBs and analytical services. Guys, this DBs and analytical services offered by the cloud. Okay, a full spectrum of this is managed services from relational databases, NoSQL databases, and various big data analytical tools. Okay, so here, so I think, yeah, somewhere we have not mentioned that, but yes, it is important. DBs analytical services. And you can see one more very, very important that is called as centrally managed via console. Centrally managed via console. Somewhere we have taken that point. I don't know where it is mentioned. But yes, guys, let me explain you this. See, I think it is there in yeah, somewhere. Yeah, here. Centrally managed via consoles. Guys, all these services are managed via a single web interface or through command line tools and APIs. So this is the example I'm showing you all, guys. Maybe you all seen this. So this entire environment gives us a flexible platform. Okay, so now let us zoom in on the what compute part. So this is the compute part one. See, focusing on the traditional compute layer, so which is typically your infrastructure as a service virtual machine. So here are the key operational points, guys. The very first point is called as pick and launch. Okay, so guys, you start by selecting a set of machine specifications. Okay, CPU, RAM, network performance, everything. And along with that, the desired operating system environment. You then launch this. Okay, you launch this instance within a specific region and an availability zone. That's all. The first thing is done. And what about the second thing, guys? Configure security profile. Guys, you immediately configure the security profile. So primarily using firewall rules. So here we have to use some firewall rules. So this firewall rules, what? Formed via security groups. So that will allow or deny specific network traffic, guys. See, for example, allow HTTP traffic on 80880, but deny all other ports. Okay. And next one is fault tolerance. The third very, very important thing is fault tolerance. You can achieve high fault tolerance by choosing to deploy multiple instances across different regions or AZs. So this is the key to building resilient big data cluster. And we have next one, Elastic IP. So maybe, yes, you people are aware of this. To ensure that a service remains accessible even if the underlying instance fails. You can use elastic IPs like static public IP addresses, so on and so forth. If an instance in one AZ fails, you can quickly reassign the elastic IP to the new one. Okay, so healthy instance in another available zone also. So your users or other services don't see an address change. And the last very, very important one is auto scaling. Guys, auto scaling for what? Handling fluctuating loads. Okay, you create new instances on the fly using auto scaling or manually add new instances to the load balancer. So this is the traditional fully managed VM approach, guys. So now we are looking at the next evaluations of cloud compute, that is serverless. Okay, now I'm talking about serverless. Look at here, guys. Guys, creating and running a cloud applications, even on infrastructure as a service, still requires managing a lot of components. The core code, libraries, integrations, event triggers, databases, containers, networks, so on and so forth. So users still have to manage and configure some of this. So the question is, how can we simplify this further? Okay, the answer for this is, guys, see here, the answer is given here. Simply infrastructure management and services. Sorry, simplify infrastructure management and servers. So especially in large scale deployments, guys. So this leads us to serverless platform. What do you mean by serverless, guys? Serverless does not mean no servers, guys. It means you don't manage them. The cloud providers takes care of all the management, all the scalings and also configurations. So the example also given here, you just go through the example mentioned here. So instead of setting up a traditional databases on a VMware, you use a serverless DB. So that is like managed DynamoDB or serverless Kubernetes clusters. You only focus on your core code and also microservices. Okay, the ultimate form of serverless compute for big data is to adopt function as a service and event driven programming model. So this is where we run small pieces of code in response to the events. Now let us look at what is that FAAS, function as a service. Guys, function as a service is a revolutionary way to host code. It allows you to run code at the function level where the user is abstracted away from the underlying infrastructure need to run that function. See example, the most prominent fast platform is AWS Lambda. Okay, this is the best example actually. Okay, and let me take the example of pricing model. Guys, the pricing is incredibly granular, right? You pay only based on the number of requests, the duration of the function execution, and the maximum memory you allocate. If your function runs for 100 milliseconds and uses 128 MB of RAM, you are billed for exactly that tiny amount. So if it sits idle, you pay nothing. Then what are the key characteristics of this? The very first key characteristic of this is stateless. I think everyone will agree with my point. Guys, fast functions are inherently stateless. The meaning of this is they cannot rely on data being preserved between one execution and the next. So this is the first key characteristics of fast. And what is the second characteristics? Guys, this is the second characteristic. You pick from a set of runtimes like Node.js, Python, Ruby, and you specify memory requirements and also timeouts. Simple. And the third requirement here is constraints. Guys, let me talk about constraints also. Okay, so here, this is the third one. Guys, what I would like to say now is, guys, fast platform have limits on resources and execution durations. Okay, so the state has to be managed externally in the database or in a file store. So they are not meant for complex functionalities. See, they are not meant for complex means what, guys? Long running functionalities like huge hour-long batch map reduce job. They are best for microservices and also event handling. Okay. And yeah, the real power of fast comes from its event-driven nature, guys. So which we are going to see in the next slide. Look at here. Here I have mentioned few points on this. So how does a fast functions executes? You can ask this question to me, right? The key is the what event-driven programming model. Okay, guys, a function executes only when it is triggered by an event. I hope everyone will agree with my point. So that point I have mentioned here. Okay, so it is a fundamental shift from a server that is always running and waiting. Okay, so later look at the what types of triggers we can have. What are the different types of triggers we have? The very first trigger is a REST API call. Guys, a request comes through an API gateway. So which immediately executes the functions to handle the request. So this is perfect for the backend of website. And the second one is a file upload. Okay, this is the second trigger point actually. So this is a huge big data. This is for what? Huge big data, guys. When an image or log file is uploaded to the cloud storage like AWS S3 bucket, so it can trigger a Lambda function. So here it is triggering a Lambda function. Okay, so that function can then automatically process the image or parse the log file or creating an automated data pipeline. Okay, and third one is time expired. A time expired. Guys, a scheduled event like a cron job can trigger the function to run every hour for reporting or maintenance. And next one is a message arrival event. Guys, a message landing in a queuing service. So usually we are going to use Amazon SQS. Let me write here. Amazon SQS. Or we can use streaming service. So these can trigger the functions to process that message. Guys, so what I would like to say here is fast functions acts as glue. Remember this. Connecting various cloud services. So it will connect with storage, databases, queuing for input or output also, guys. So it is an architecture of services talking to functions. Now let us look at the second major pillar of our architecture. So that is called as networking. Okay, so now we are talking about networking concept. My dear friends, in big data, data must flow securely. Hope everyone will agree with my point. That is where the virtual private cloud comes in, guys. So in short form, we are going to call it as VPC. Guys, a VPC is essentially a private space offered on a public cloud. You can think of it as your own isolated, secure virtual network within the massive public cloud infrastructure. Okay, so here I mentioned ideal for hybrid cloud deployment. So it is the foundation for hybrid cloud deployment. It is allowing you to securely connect to your on-premise data centers to cloud resources. And the second point, user control and isolation. Look at here. User has control over network within VPC and create isolation. So you have complete control over the networking within your VPC. So this allows you to create isolation between different application components. Okay. And next we are talking about subnet. Maybe you have heard about subnet. The VPs are divided into subnets. So which are ranges of IP addresses. So under that, what do we have, guys? So we can have private IPs, or we can call it as public subnets, private subnets. What do you mean by public subnet and also private subnet, guys? Public subnet is nothing but what? See, this is nothing but the resources need direct internet access. So best example for public subnet is load balancer or web front end. And what about private subnets? See, it is an instance, internal resources like databases or sensitive processing clusters that should not be externally accessible. That is called as private subnets. Okay. And sometime, yes, guys, we are going to talk about network address translation. Or sometime we are going to talk about VPNs. Network address translation. So multiple private devices can share a single public IP to access the internet. So for that, you can use what? You can use VPN, right? You can use VPN, virtual private network. So that is to secure external access or to connect your enterprise network. Guys, in AWS, subnets are tied to single availability zones. So this is important for fault tolerance design, guys. You set up your compute and storage services inside these secure subnets and manage your IP addressing with elastic IPs. Okay, now let us look at the next layer of networking. What is the next layer of networking? That is called as external connectivity. Okay, external connectivity. Guys, moving beyond the VPC, we need to consider two critical external networking components. The very first one is called as DNS and second one is called as VLAN. What is DNS, guys? Domain name service. Correct? No? So for any internet-based applications, you need a service to translate your human readable name to an IP address. Okay. The best example for this is AWS Route 53. Okay. So this is highly available and scalable DNS service that can manage traffic routing, latency, and even platform health checks on your services. Correct now. And what is the next one? The next one we are talking about VLANs, VLAN services, virtual local area network. Guys, if you are running a hybrid cloud and you want a dedicated high-speed secure private connections between your on-premise data centers and your cloud, means you use dedicated connection service. Understanding? So the best example for this is AWS Direct Connect. So this bypasses the public internet and it is going to offer a more consistent and low latency network experience for transferring massive big data sets. Okay. However, guys, getting this setup requires checks on the cloud location support, the capabilities of your enterprise router and also physical link types. So my dear friends, so we have covered the core architecture for computers and also network. Now let us recap before diving into the best practices. Okay. So this is the recap given here. Okay. So yeah. So let us look at here, guys. So we laid the group. See, we understand the cloud concept. And also we have reviewed the infrastructure, compute and network, including infrastructure as a service, function as a service, VPCs, everything. So next, so perhaps most practical part of our session is dividing into best practices. So this is the how to section. So how do we take the building blocks we just learned about and also assemble them into a system that resilient, scalable and secure? Guys, here we are talking about architecture patterns that all major cloud companies use. Okay, so we start with the most important characteristics of cloud, guys. What is the most important characteristic of cloud? So that is nothing but elasticity. We are starting with automated elasticity first. Guys, automated elasticity is what distinguishes a cloud applications from the traditional application. Correct, no? So here the goal is simple, guys. Applications can provisioned with resources on demand when they need it. Very simple. Your big data processing spikes at midnight due to a data injection job. The system should automatically scale out. When the job finishes at 2 a.m., so it should scale back in. That's all. Very simple. Okay, guys, achieving this requires you to rethink your application design. You cannot just lift and shift an old monolithic applications. Correct? No. You must understand. See, here I've given the 2 points. You must understand which application component can be elastic. So is it your web front end? So is it your batch processing cluster? Or is it your message queue? And along with this, you must also consider the impact on overall application being elastic. See, for example, if you quickly spin up 100 compute nodes, can your database handle 100 new connections instantly? Correct? No. So this points to the need for decoupling. So which we will cover shortly, guys. Okay. So the best way to achieve elasticity and reliability is to build on the assumptions that failure is inevitable. So let's look at how we design for that, guys. Okay, look at here. Guys, this is a very, very important concept. Okay, this is a very, very important concept. Okay, see, on the cloud, we don't design to prevent failure. We design to handle failure gracefully. Okay, so components will fail, guys. So server will idle. And sometime AZs can have power issues. Correct? No. Yes or no, guys? I'm telling you the truth. So here are the critical techniques. So what are those critical techniques? The very first one I'm talking about, use elastic IP. Guys, already we have discussed about this, right? So this static IP can be mapped to the healthy server to quickly recover service. And along with that, we use multiple AZs. So always deploy replicas of your services across different availability zones. And if one availability zone fails, your application continues to run in another one. And third one is maintain images. Guys, create and maintain standardized machine images. So like your Amazon machine images. So these are golden copies of your operating system and application configurations. If a server fails, a new one can be cloned from the image and restored quickly. And next one is use monitoring services. Guys, services like AWS CloudWatch are essential here. Correct? No? AWS CloudWatch is essential here. They monitor resource metrics and they monitor, not only monitor, it is going to trigger automated actions or alerts. And along with this, so we have to create auto scaling groups. So these groups automatically replace failed instances quickly, and which is going to ensure the desired number of healthy instances is maintained. And finally, don't forget to do this, guys. take snapshots and backups. So this is your job. So regularly take snapshots of your block storage and backup them up to what? Highly durable external storage like S3. So this is your ultimate safety net for recovery. Okay, guys, the concept of decoupling is central to both elasticity and failure design. Okay, so here I'm talking about decoupling application components. Look at here, everyone, guys. Guys, decoupling means what? So decoupling means breaking down a large application into smaller or independent components. So this is a what fundamental concept in modern cloud architecture, right? Especially for big data pipelines. Am I right or wrong, guys? So you use interact. See here we have to what interact using queues. Okay. So this is the best way, guys, to decouple is to have application components communicate with each other using message queues. Already I've told you about AWS queues, right? Same thing. Or you can use Apache Kafka also, guys. Okay. And next one is streamless components. Oh, sorry, stateless components. Okay. So design your application components to be stateless as possible. And the meaning of this is a server can handle any user's request because it does not store user specific information locally. Okay, then what is the benefit of this? Guys, the benefit of this is a stateless component can be scaled out or replaced instantly by a load balancer because it requires no complex session transfer. And finally, we have one more point here. What is that? Store any session state in DB. So if you want to maintain state, okay, so store it externally in a highly available databases. Okay, guys, decoupling is the key to next best practices. What is the next best practices we are discussing here? Automation. Okay, automation infrastructure. So automation is the final piece of cloud architecture puzzle. So we want to automate everything from deployment to scaling. So the very first one is auto scaling is the key. Auto scaling is the key, correct? No? Automation is the key to achieving auto scaling. You create auto scaling groups for different clusters. That's all. And next one is monitor for resources. Guys, you monitor resources like CPU, memory, input, output. If your CPU of your cluster is consistently high, the monitoring service triggers an action to launch new instance using standardized machine images. And third one is configured data used. Configured data in databases. See, whatever the configuration you're doing, guys, all the configuration data used for this automations. Okay, so it is like parameters, threshold values, deployment scripts. See, all these should be what? Stored reliably in a centralized databases or configuration stores. And next we are talking about build process. So a deployment pipeline should ensure the latest binaries go on the global external storage like AWS S3. Okay, and config management tools. So use powerful open source tools like Chef, Puppet, Ansible, so on and so forth. Guys, these tools automates the configurations of newly launched instances. See, for example, they can install dependencies, set up user accounts, and start the applications. And one more is location independence. Where do we have location independence? So this point is explaining on location independence. Okay, so finally, guys, your application component should not depend on the specific location. It should not depend on the specific location. See, here I have mentioned that point. Correct, no? Or it should not depend on particular hardware, or it should not depend on IP addresses. Since an image or binary can be moved anywhere on failure, the application must be designed to discover its dependencies dynamically. Okay, the final best practice we must cover is the most important one is security, guys. See, in last slide, I'm talking about security here. Okay, my dear friends, see, security on the cloud is fundamentally different. Okay, and very important point. The traditional enterprise perimeter security does not work on cloud. So security needs to be what? Integrated at every layer of application architecture. Guys, we must focus on two things, guys. The very first thing is, this is the first thing I mentioned here. Protect data in motion. And the second one is protect data at rest. Okay, so for protect data in motion, so we are going to use encryption. We are going to use isolation. We are going to use secure connections. So encryption, we are going to use SSL certification and encryption for all data movement. For isolation, we are going to use VPC to isolate your resources. And for security connection, we are going to use secure VPN. And what about protect data at rest, guys? So here also we are going to use encryptions, right? So you must encrypt files or entire storage volume. And the second one is key management. So the key management is critical here. You must use a robust key management service. So in short form, we are going to call it as KMS to secure your encryption keys and ensure they are not lost. Understanding my point, guys? So these are the 2 points you have to remember for a long time, guys. And what about access control and firewalls? Guys, the very first point here we have to remember is Identity and Access Management Service, IAM. Guys, use the robust IAM service provided by the cloud provider to manage users, roles, and permissions. Okay, and second one is instance specific virtual firewalls. So it is like AWS security groups for individual compute instances, load balancers, databases. And along with that, you have to use subnet level access control. So which is also called as subnet firewalls. So don't forget to use network ACLs, guys. So access control list for subnet level access control. And finally, so we have application firewalls, web application firewalls. Okay, so we use this WAF along with load balancer to block application specific attacks. So like SQL injections or cross-site scripting, we are going to use this. Guys, a layered approach is the only way to ensure security on the cloud. That you should remember. Okay, so now let us look at the conceptual applications to tie all these practices together. So this is one conceptual application we have taken here, guys. You just imagine. So we are designing a highly scalable parallel search applications that crawls and indexes the web. So we will call it as grep the tech. Okay, we are going to call it as grep the web. Guys, we need to run a parallel search applications for multiple users using the cloud best practices architecture. So how do the concept we just learned apply here, guys? So the very first one is storage. Guys, we would store crawled URLs on a global storage. So what we are going to use, guys? So we are going to use S3. Okay, so this is our massive decoupled data lake. And next, what about querying? So what about querying, guys? So querying, see, when a user submits a search query, that query is placed into queuing service. See, we have a queuing service here, right? Amazon SQS. So this decouples the search submissions from the actual search execution. And next one, we are talking about clustering. Okay, a pool of compute instances will read from the queue and execute parallel search against the data lake in S3 and then return the result. So this cluster would be managed by an auto scaling group for elasticity. And next we are talking about DB to manage metadata. Guys, we use a high performance DB to manage metadata. So such as index structure itself and user authentication data or crawl history. So DynamoDB would be a what great fit here, guys. And the last one we have monitor. Okay, last one we have monitor here. So we use monitor service, or we can call it as CloudWatch, to track the health, latency, and resource utilizations of all these components. Okay, so this design ensures the system can handle burst of millions of search queries while maintaining reliability. Okay, so here we have taken one examples, guys. You just go through this example. I'm not going to explain this example for you people. Okay, so this is showing you what conceptual flow up to our grep the web discussion. I want you people to visualize the flow, guys. So here, what do we have? So we have injection. Okay, so ingestions are nothing but what crawlers we are using here. And then we have indexing cluster. So we are using EMR, or we can use Spark also. We have search front end, search cluster, everything, guys. Queue concept. So this clear separations of concern enabled by cloud services is what makes the what system scalable. Okay, so now let's turn tables, guys. So I have a what system design exercises for you guys. So this is again one more homework I'm giving for you all. You just go through this system design exercises. My dear friends, so let's put on our solutions architects hats. Okay, I'm requesting each and everyone. So you have to what? Put on solution architects hats. The challenge is to design an Instagram as a cloud native big data application. Okay, so this is how you go about creating a design, guys. So what you are going to do very firstly, so you are going to identify big data requirements first, correct? No, that is the first thing, right? So what kind of data is involved? Images or videos or user generated comments, likes, or profiles or hashtags relationship. So you first identify the big data requirements. And the next, think about storage. Okay, so what kind of storage would you need? And you will need an object storage for the what actual images or videos. And you will need NoSQL databases, or you need graph databases. So secondly, you have to decide on storage. And third thing is you have to decide on consistency. Correct? No. What is the desired data consistency? See, when a user posts an image, does everyone need to see it instantly? Or can it be what's seen eventually? See, eventual consistency is often okay for social media feeds to prioritize availability, right? So you have to think on that. And after that, you have to think about computations. Okay, you need compute instances for the API. Not only for API, guys, you need load balancers, messaging systems, okay, and about caching layer. Okay, and think about this, guys. So how are users served? How are notifications sent? And what APIs are needed? So this exercise encompasses everything we have learned today. I hope everyone understood this. So this is a summary. I don't want to go with a summary. So is this crystal clear to everyone? Is this crystal clear to everyone? Shall I get quick responses? So we have learned different cloud models and different types of services. We have learned key best practices. So we have gone through what core principles like design for failures, automate, build, deployment configurations. Correct? No? For those interested in going deeper, the reference material mentioned in chapter 18 from Cloud Computing Principle and Paradigm is the best resource. So this brings us the what end of discussion on cloud compute and network, guys. So is this clear? So shall we take 10 minutes break, guys? So after taking 10 minutes break, so I will continue with 12 session concept. So is this okay for you all? Shall we go for 10 minutes break? After this, I'm going to start with next session, cloud storage. Okay, now the time is 5:05. So we'll come back at 5:15. Okay. Okay, guys. So welcome back to session 12. So we are transitioning from the compute engine to the data repository. Okay. Wait a minute. Here, let me share my screen. Yeah. One second, guys. Okay, guys. Yeah. Okay. So yeah, let us start with the the storage part. Storage on cloud. Okay, the sheer volume and variety of big data means your choice of what storage is arguably the most critical decisions in your architecture, right? Guys, today, so we are looking at storage on cloud. And we will discuss this by using AWS example. So now you can ask me, right? So why AWS? Okay, why AWS? Because they offer the most comprehensive and diverse set of storage services. So which clearly illustrate the trade-offs we need to learn and trade-offs between performance, cost, and durability. Guys, in the big data world, you can no longer use a single type of storage. You need a polyglot persistence strategy. So that is what we will be exploring now. Okay. So you all look at here, guys, storage with metadata. So before we dive into specific AWS services, so let's talk about a core concept in cloud and big data storage. So that is called as storage with metadata. Guys, in traditional storage, a file is just a file. That's it. Its name, size, location. But in cloud native big data system, the storage object is much richer. So it is the data plus its descriptive metadata. So let me take one example to explain on this, guys. So when you upload an image, the cloud object store does not just store the image. It store metadata like the data, date it was created, who owns it, and customer tags you have added. Okay, and access permissions. All these things it is going to add along with that. So this rich metadata is the key to creating scalable data lakes. Guys, it allows us to search, manage, and process data without having to read the content of the file itself. So this concept is best exemplified by our first topic. So that is called as object storage. So we are discussing object storage in the very first session. So these are the topic we are discussing in today's session, guys. So this is the agenda of session 12 to master our 4 types of cloud storage offerings. So one is object storage. So we are discussing here is S3, and second one is file storage. So here we are discussing EFS. Third one is block storage. We are discussing EBS, and fourth one is databases. So we are discussing DynamoDB. Okay, so let's start our deep dive into workhorse of cloud storage. So that is your S3. Look at here, guys. So S3, what do you mean by S3? Simple storage service. Okay, so this S3 is the original defining cloud object storage. So now you can ask me, sir, what is it? Guys, S3 is an object storage service. This means it stores data as object. Data as objects. Remember this. And which are essential files bundled with a rich set of metadata. Already I've given you the example, right? Same thing. And the second very, very important thing you have to remember here is container. Okay, guys, a bucket is the container for the object. Correct? No? An S3 account can have hundreds of buckets, and a bucket can hold hundreds of billions of objects. Then what do you mean by objects? Guys, a object can range from 1 byte to 5 TB. So it is uniquely identified by a developer assigned key and its URL. Not developer assigned key only, so along with that URL. And guys, when I'm talking about security and access, guys, each object has an ACL. Okay, so ACL is nothing but what, guys? Access control list. So this is to control who can access it from anywhere. Okay, even outside of the AWS ecosystem also we can access it, guys. And what about durability and scale? Guys, once I'm talking about durability and scale, S3 is a highly durable service. So it support versioning. The meaning of this is if you overwrite the file, you can retrieve the old version. So it is highly partitioned and replicated for the massive scale. So make a note of this, guys. This point is very, very important. I'm talking about eventual consistency. Make a note of this. Guys, S3 uses eventual consistency across multiple reads and writes. Okay, so we will discuss what this means for big data next. Okay, so let me take one example to explain on this. So this is a small example I'm taking you guys. So to visualize S3, imagine you have a digit file cabinet. Okay, you just take this example. You have digit file cabinet. The file cabinet is your S3 account, correct? No? Let me write here. File cabinet. So this is your S3 account. Correct? No? And the large drawers of your buckets. See, large drawers are your buckets here. And you can have many buckets. Okay, so in this slide, so we have taken 3 buckets. Okay, 3 buckets with folder inside bucket for a grouping object we have taken here. So inside the bucket, you can create folder. So inside the bucket, you can create the folders for organizing your objects. So this is just for organizational convenience. So S3 is fundamentally a flat key value pair, guys. So flat key value store. The files inside the folder are your objects. I think you're all getting my point, right? The key things is how to access them. You can access any objects via public URL, guys. So I have given 2 options to you all, guys. Okay, the very first option is you can use path style. See here, path style I have mentioned bucket name .s3.amazon.aws.com/object name I have mentioned here. This is one way of accessing it. And the second way of accessing it is virtual hosted style. Okay, virtual hosted style. So s3.amazon.aws.com bucket name /object name. Guys, this HTTP access makes S3 a perfect target for web applications and universe source for your big data compute clusters. Okay, now let's get into the theoretical heart of S3. So, and its consistency model. You look at here, this is the consistency model we are discussing on. Guys, this is a very important point that brings us back to the CAP theorem. So already we have learned about CAP theorem, right? Guys, S3 follows AP design. Okay. So S3 follows AP design with respect to the CAP theorem. So remember AP means what, guys? It prioritizes two things, right? A means availability and P means partition tolerance over a strong consistency. Correct, no? And one more point I have mentioned here, eventually consistency. So when a user uploads an object, so it is immediately replicated across multiple storage devices and even multiple available zones. The system is designed to return read success quickly. So, but readers may access inconsistent replicas temporarily. See, all replicas are eventually consistent here. So let us look at the practical implications, the observations. What are the observations I have mentioned here? The very first observation I have mentioned here is stale data on read. Stale data on read. Guys, if one user writes data and another user reads it immediately from a different replica, the render may get old data. Understanding my point, guys? The render may get a old data. And second one is missing keys. Okay, second point I'm discussing here is missing keys. Guys, user uploads an object, but a reader may get a what? Key does not exist error for a brief time. So this is the point I'm explaining you here. And delayed listing. The third point is delayed listing. What do you mean by delayed listing? Guys, an object may not appear in a bucket listing immediately after being returned. Understanding? And ghost delete. The last point I'm telling you about ghost delete. Guys, a deleted object may still be seen in a listing for some time. That is called as ghost deletes. Okay. Understanding my point, guys. Guys, S3 used to offer reduced redundancy storage. Here I've mentioned reduced redundancy storage. So in short form, we are going to call it as RRS option for lower cost where writes or update might not be durable. So this is a classic big data trade-off, guys. Lower durability for reduced cost is the classic big data trade-off. So despite the eventual consistency, so S3's scale and durability are unmatched. And it is the right trade-off for most big data batch processing where data staleness of a few seconds is acceptable. Okay, so let us look at the architecture now. So how does S3 achieve this massive scale and durability? Guys, it is all about the physical architecture. Okay, so look at the physical architecture here, everyone. So the very first thing I'm talking about, global footprint. Guys, cloud providers operate in many regions. Okay. So cloud providers operate in many regions. So 20 plus regions with multiple availability. And along with that, the second point is isolated AZs. Isolated available zones. Guys, each region has multiple available zones. So remember, AZs are physically isolated data centers, right? Connected over a private and low latency network. That you should remember. And one more thing is high durability by default. Okay, so critically S3 is designed to store data in at least 3 physically separated AZs within a region. So why this is, guys? So this provides high availability. If one AZ is destroyed, your data is safe in the other one. And the very third point we are discussing here is scale. Okay, the combination of many regions and many AZs. Okay, you better take each AZ can have what up to 8 data centers, right? Use the combinations of regions and also many AZs. So that will provide the backbone for S3 near infinity scalability. Guys, this highly distributed replicated architecture is the reason you can trust S3 with your most valuable data. Understanding my point? Then what are the features of this architecture? S3. Guys, the very first feature here. See, I have mentioned here is storage tiering. What is storage tiering, guys? This is a critical for cost saving. You can set up policies to automatically move data to lower cost storage classes. So as it ages and becomes less frequently accessed. See, for example, move logs older than 90 days to an archival tiers actually. And the second feature is object lambda. So this is one of the incredible feature we will discuss next. It allows you to add compute to your data storage. And the third one is access points. Third one we are discussing about access point. You can create specific endpoints with associated ACLs. Okay, for your customized client access. So this allows you to simplify and secure access to specific subsets of data. And the last feature is batch mode operations. So this allows you to perform large scale automated operations on millions or billions of objects, such as copying them, updating their metadata, and applying retention policy, each and everything. Guys, these features move S3 from being just a storage container to a highly intelligent data platform. Okay, so let us talk more about storage classes. See, look at the diagram, guys. So see in this slide, so it is a setup for our discussions on how we manage the cost of big data storage. Guys, we all know, right? The cloud offers different storage classes based on your access patterns. So this is the classic trade-off, guys. So what you have to remember here, the very first thing is you have to remember on faster access by higher durability. Let me write here. Faster access by higher durability. What is this, guys? So this is equal to what? Higher cost, correct? No? This is equals to higher cost. And slower access by archival, that is lower cost, obviously. So we will see this classification applied to other storage types as well, guys. So let's quickly touch upon the concept of S3 outpost first. Okay, see here. Once again, guys. So S3 outpost first. Okay, so everyone look at here, guys. Guys, remember hybrid cloud model. Guys, S3 outpost is a physical manifestations of that model, correct? No, it enables you to literally have a rack of AWS hardware managed by AWS placed on your customer premises. So what is the benefit of that? The very first benefit is faster local access. And the second one is local residency requirement. Okay, you get best of both worlds, guys. The S3 object store interfaces and APIs, but the data is physically on your premises connected to your VPCs. That's it. Okay, so now we are moving forward and talking about object lambda. So this is one of the coolest recent development in cloud native big data, guys. It combines two concepts we discussed. So what is that? The very first thing we have discussed about fast, right? And the second thing is S3. So it is combining these two actually. So FAAS is combining with S3 storage. Okay, remember fast. So we said it about moving the compute closer to the event. So what if you could move the functions closer to the data? That's the idea behind object lambda, guys. So it allows you to add code to an S3 GET request for data processing. Okay, so let me take one example on that. Yeah, here we have an example. Look at here, guys. A user requests a file by using this statement. get space slash my images JPG. Okay, so before the file is returned, a Lambda function is triggered here. Okay, the Lambda function can transform the object. See, for example, it could redact all the personal identification informations from the log file and convert a TIFF. Okay, so convert a TIFF image to what? JPEG image, and dynamically resize an image based on the requesting device. And next point is, see, the transformed data is then returned to the user. The original object in S3 remains unchanged. Guys, you register an access point with a Lambda transformation function. This allows you to customize the data delivered to different applications without managing multiple copies of the data. So this is a powerful serverless way to execute your data processing logic, guys. Okay, so now let us look at one use cases. See, we have plenty of use cases here. You just look at here, guys. So why is S3 is so important for big data? Guys, it is the foundation for multitude of use cases. Okay, so the very first one is I'm taking here is backup and restore. So it is highly durable, guys. Low cost destinations for backing up your data, both from the cloud and from on-premise data center. So this is the very first use case. And the second one is disaster recovery. Okay, so its ability to replicate data across regions. Okay, that makes it ideal for building robust disaster recovery solutions. And third one is data archival. Okay, so for regular means what? Regulatory compliance, data that must be kept for 7, 10, and 20 years is moved to the lowest cost archival tiers of S3. Okay, and fourth one is cloud-based applications. So it provides scalable storage access from anywhere for cloud native applications. And finally, it creates data lakes for big data analytics. So this is the big data killer feature. Okay, so S3 is the single centralized massive repository for all your raw processed and refined data. So it's serving as the core. One second, guys. It's serving as the core of your modern data lake architecture. And one more thing is, so S3 object storage. Now let's shift to the different paradigm. What is that paradigm? So we are talking about the second one, that is file storage. Guys, today I'm going to complete only file storage. So tomorrow I'm going to complete these two concepts, guys. So I'm not going to complete the entire concept in today's session. So I'm going to complete till here only. Okay, so later on I will stop my discussion. Guys, let us go through a quick recap. So we have just completed a detailed dive into object storage, right? So now we are moving on to two other critical storage types. So one is called as file storage. So in short form, we are going to call it as EFS. And second one, we are talking about block storage, that we are going to call it as EBS. So these two services addresses use cases where the object storage made of HTTP access just is not suitable, guys. We need more traditional low latency disk access for certain types of applications. Now let us start with the very first one, that is EFS. Okay, guys, what is EFS? What is EFS, guys? Elastic File System. So this is the cloud's answer to traditional network attached storage or shared file servers. So you can ask me, sir, what is it? EFS is a file system built using SSD storage. Okay, so it is a file system built using SSD storage. Then what is the purpose of using this? Guys, the purpose of using this is to be shared file system that can be accessed from multiple cloud instances simultaneously. Understanding? And what about protocol? Guys, it support the standard NFS protocol, Network File System Protocol. Then the benefit of using this is, guys, applications can simply attach the file system within a VPC. This means if you have an older legacy application or a Linux utility that expects a standard file system mount point, you can use EFS without changing any code. Clear? And what about elastic scalability? Guys, it gives you elastic scalability in storage capacity and throughput. So it offers high performance up to 10 GB per second and 500K IOPS. Okay. And yes, guys. So let me take one example for this, guys. So big data use case. Guys, it is perfect for sharing scratch space for a cluster of analysis server, or for content management systems where multiple application servers need to read and write to the same file hierarchy. So like S3, EFS also comes with different storage classes to manage the cost. What are those? See, here we have a different storage classes. Guys, managing storage cost often comes down to matching the data access frequency to the right storage class. So EFS offers two primary types. So this is the first one. One is standard and second one is one zone. Okay, so let me start with the very first one, that is standard. So standard is also called as EFS standard. And second one is EFS standard infrequent access. So let me start with the both, guys. EFS standards and EFS standard infrequent access. EFS standard. Guys, this EFS standard is high durability options with replications to 3+ AZs. So this is for your frequent access mission critical data. And what about EFS standard infrequent access? Guys, this is for data that is durable but accessed less often. So typically 80% of files fall into this category. The cost is lower here, but you pay a small retrieval fees when you access the data. So this is about standard. And the second one is called as one zone, guys. One zone classes. So under this, we have EFS one zone and EFS one zone infrequent access. So let me start with the very first one, EFS one zone. Guys, this class is replicated for durability only within 1 AZ. Okay, so it is a lower cost option, but this offers less resilience than standard class. And what about the second one, EFS one class infrequent access? So the lowest cost option for non-critical, rarely accessed data, we are going to use the second one. Okay, so you can set up lifecycle policies to automatically move data based on its age from the standard to the infrequent access class. So which is ensuring you always optimize your storage spendings. So let's quickly visualize the deployment of EFS in the cloud. See, this is the standard storage class. So this slide helps us to visualize the EFS standard storage class within a typical VPS setup. Okay, now what I would like to say is, guys, you imagine your VPC has 3 available zones. Okay, your VFC has 3 available zones because EFS standard class is highly available and replicated across multiple AZs. You need to connect to it from any of your compute instances. For this connection, you create a mount target in each AZ, guys. In each AZ, you are going to create a mount target. Then what is mount target? A mount target is simply a network endpoint that allows your EC2 instances within that AZ to access the EFS file system. Then what is the key takeaway here? The key takeaway here is that for best performance and cost, your compute instance should access EFS from a mount target within the same AZ. While EFS is replicated across all AZs, accessing it across AZs would introduce higher latency and incur a data transfer cost. Okay, so now look at here. So we are continuing with one zone storage class. One zone storage class. Guys, one zone storage class simplifies the architecture and saves cost, but with what trade-offs? With the one zone class, you only have single mount target in one AZ. Then what is the trade-off here? Guys, if your compute instance is in another AZ, it has to pay for the data access cost and will experience highly latency because the data must travel between AZs. More importantly, if that single AZ fails, the data is unavailable. So when do you use that one zone? See, for development environment, for test data, for data that can be easily read generated, you can use this one zone. Okay, you would not use it for your mission critical productions data lake, guys. And finally, this slide asks for this, guys. What if, see, look at here. What if you have connect customer premise? So you would use the AWS Direct Connect or VPN service to securely connect your on-premise network to the EFL system within your VPC. So this is creating it as just another shared folder on your local network. Okay, so that will complete your first concept, guys, file storage. So this block storage we can discuss in upcoming class, guys. Okay, so this block storage concept we can discuss in upcoming class. Is this okay for you all, guys? So I'm going to stop the session. So since it is my second class, so it is very difficult to talk more about theory concept, guys. Is this okay for you all? Shall we continue the next two concepts in the next coming class? That is in tomorrow's class. Okay. So that's all from my end, guys, for today's session. Thank you so much for your active participation. And if you have any questions, so please post them on the forum. So now I'm not able to answer to your question. So do we have lab for S3, EFS, EBS? No, only we have lab on S3. That's all. So that is how to create S3 and how to store. That's all, guys. Not much. Pradeep. So one program you have on S3, but I'm not giving any assignment questions on S3. But as I told, once your virtual environment is not supporting for lab, then you can go for AWS. Sir, why S3 is called object storage compared to EFS? Yes, Gautam is asking very good question. Can anyone answer? Can anyone of you answer to Gautam's question? I think that point I've discussed, right?
Yes, sir. Should I answer?
Yeah. There is a disturbance from your end.
Yeah, because some of the work I was doing in my house. Yeah, so S3 is a simple storage service. So in which the data is stored in the form of object. And in EBS, the data is data is stored in the form of blocks. So it is EBS simply.
Yes. Gautam, have you understood? Why S3 is called as object storage? The reason is it stores data as objects. Correct? No, that is the main reason. So which are self-contained units of data that includes the data itself. So metadata and unique identifiers, so on and so forth. So this allows for efficient storage and retrieval of unstructured data like files, images, videos. Okay, but EFS is a file system that stores data in a hierarchical structure. That's it. So with files and directories. So EFS is mainly designed for use with EC2 instances and other AWS services like providing shared file system, so on and so forth. Clear, Gautam? Yeah. So any other questions? Thank you all, guys. So thank you all. So no questions means we can stop the session. Can we do our part 2 assignment with S3? Pradeep, you can do wherever you want. So as I told, you have to define the problem from your organization. That's it. So solution, see, my first priority is you people have to use the cluster provided by the BITS Pilani. Okay, once there is a problem with network or problem with lab, then you can go for private one. So even they are providing AWS also, right? So even in AWS, you can solve all these problems. Correct? No, Pradeep? So have you all started? Have you all started working on assignment? Guys, you have very small amount of time. The last date to submit your assignment is 18th October. Sorry, 18th November. Okay, so maybe you will be in 15th session. So after that, see, before 16th session, we have to submit your assignment marks. So for that reason only, I'm asking you, I'm not going to give you extension. So please do complete within that given time. Okay. Even quizzes reopened. So anybody has missed your quiz too. So please to complete your quiz by tomorrow. Okay. Yeah, that's all from my end, guys. So anyway, we have a session tomorrow. So in tomorrow's session, we are going to discuss half of your 12th session concept and also 13th session concept. So bye. See you guys. So see you in tomorrow's session. Have a nice day, guys. Bye-bye.